I'm Bill Kinney from Bethel University in St. Paul, Minnesota, and this is part 7 of using Mathematica for ordinary differential equations. I thought of a great subtitle for this particular video based on the content. I'm calling it a smorgasbord of miscellaneous Mathematica and mathematical subtleties. Doesn't that sound delicious? Everybody really excited? Well, okay, it might not be real exciting. We're going to be talking about subtleties, lots of detailed distinctions between things to try to hopefully dispel some confusion. But because they are subtle, they are going to be confusing by their very nature, and so you're going to want to do your very best to psych yourself up and pay attention and maybe pause the video and take notes and try things on Mathematica to help you understand what's going on here. So here is a description of all the things going on here. In the last video I introduced the use of DSolveValue. We'll continue that along with more discussion about pure functions in this video. I'm going to introduce the use of some operators, something called the Prefix Operator, the @ symbol, a Postfix Operator, // and ReplaceAll /. with rule, arrow. Don't worry about what these mean at the moment. We'll get into that. I'll show you how to use the numerical approximation function, capital N, in those contexts. We will get back down to thinking about differential equations and slope fields as well. And in that context, we'll think about focusing on just a piece of the graph that contains the initial condition when it's got a vertical asymptote, and we'll try to sort of make the graph as ideal as possible using something called the conditional if function that does certain things versus other things depending on whether a certain expression is true or false. Alright. I thought it'd be good. Well, first there's a note I want to make. In the last video, when I did this warm-up example, I accidentally wrote the word autonomous here, and I want to correct that. This equation is not autonomous. The right-hand side has got a t in it. It's got a dependence on time, so that's non-autonomous. That's what I should have written there before. It's a pure antiderivative problem. All right, here we get into the content now. I thought it would be helpful to perhaps go through some analogous mathematical subtleties related to the Mathematica subtleties we'll talk about. Alright, so listen carefully. Think with me here. Consider this kind of equation. Y equals f of x equals x squared. Okay, the typical kind of equation you'll see in a pre-calculus class or algebra class. What do you when you see something like that, various kinds of light bulbs or alarms should go off in your mind. Okay, this is a function. Y equals f of x equals x squared. That's the way you would typically think of it. Alright, but we need to get into some subtleties about some terminology and some conceptual distinctions here to truly understand what's going on. Sometimes these subtleties are important and sometimes they're not. In this equation, x and y are called variables. Alright? X is the independent variable, also called the input for the function, and y is the dependent variable, also called the output for the function. Variables can be replaced by things. They can be replaced typically by numbers or by symbolic expressions. You can replace variables with things and then work with those quantities. The expression, well, the thing on the right side here, x squared, is called an expression. Okay? Things involving variables like that are often called expressions in math. And this expression has got meaning. It's representing the square of the variable x, and if you replace x with a number like 5, it represents 5 to the second power, which is 25, 5 times 5. X squared is not the function. What's the function? F itself is the function. F itself, the letter F, is our symbol for the function name. More abstractly, it is the symbol that represents what you call the abstract rule of assignment. This idea of taking a number as input and squaring it to get a number as output. 5 squared is 25. It's that idea that F represents, in a sense, the abstract rule of assignment. This thing here is not really the function. I emphasize that down here. F of x equals x squared is not, technically speaking, the function. What do I mean there? Because oftentimes you will hear a teacher say that's the function. Well, no, technically speaking, it's the function output at the input x. When x is a number, then f of x equals x squared will represent a number. It represents a number when x is a number. It can also be thought of as a formula. It's a formula that's not the function, it's a formula that defines the function. It defines the rule of assignment to take a number and square it. Okay, so those are some subtle mathematical ideas that are kind of similar to the subtle Mathematica ideas that we're now going to talk about related to DSolveValues and these prefix, postfix operators, that kind of thing. So here's a new warm-up example here for video number 7. This is autonomous, okay, no mistake here. dy dt equals 3y, the right-hand side just depends on y. Y of 0 equals true. Alright, so DSolveValue is this new Mathematica function for Mathematica 10 and beyond. It, in some ways, is a bit easier to use than DSolve is. Let's go ahead and type in this initial value problem, y prime of t equals 3y, but you need to put y of t on the right-hand side in Mathematica, even though you don't see a t there on the right-hand side of the differential equation. Need to use double equal signs, don't forget to do that. You'll get mistakes if you forget. You can put y of t here after the comma, and then put a t, and this will give an output that is an expression, okay? An expression representing the answer. There it is, 2e to the 3t. That really is a mathematical expression, just like x squared is a mathematical expression. It's not really, as is, a function. If I give this output a name, if I call it sol, and try to plug in a number into sol, something funny happens. Okay? Sol represents this expression here, and so we're not getting what you would want to get by doing this. You're not getting 2e to the 3 times 3, 2e to the 9th. You're getting this expression somehow evaluated at 3, which Mathematica doesn't know what to do with it, really. Is there a way to plug in the number 3 into this? Yes, you can use this slash dot operator, ReplaceAll, in conjunction with the rule operator. If you go sol slash dot and then t arrow 3, so I'm combining those two operators, that will calculate this expression value when t is replaced by 3 or 4 or whatever you want to replace it by. Okay, so it's a subtle thing here. I could, instead of doing it this way, I could do it like I did in the last video. I could get rid of the square brackets here and call that sol. But that's a different thing. That's really like the function name, in a sense. That's like the f up here. This is, in a sense, an abstract symbol that represents the function, and it's stored in this sol value, and now I can evaluate sol at 3 in the usual kind of way. 2e to the 9th. There we go, just like we wanted. You can also do what are called prefix or postfix operations to do this calculation. The at symbol is the prefix operator. Instead of using square brackets as an alternative that is sometimes useful, I can do sol at 3 and get the same answer. So that's a prefix operator, this at symbol, because it goes in front of the thing I'm operating on, prefix. You can also use sol as a postfix operator, slash slash, that's the postfix operator here, right there. So I can go 3 slash slash sol and get the same thing. You can also use the capital N as a prefix or postfix operator. Again, this is a postfix operator because I'm applying the function after the thing I'm applying it to. I'm typing it after that. I can do slash slash capital N after this and get a numerical approximation for that. Or I can do these things prefix. I can do n at sol at 3 and get the same thing. Okay, so some subtle things to know about Mathematica. I don't typically make use of these things too often, but I thought it was worth bringing up. I guess I should also talk about plotting quickly with this. If I plot sol here as this pure function, again, I forgot to mention here, this is called a pure function in Mathematica. Pure functions are when you can represent functions without giving them names. Even though I am giving it a name here, I could represent it without giving it a name. I could do this, evaluate this at 3, like that. I did give it a name. I called it sol. And when I type it in like this, if I want to plot it, I need a t in here. There we go. If I go back to the original thing that I did and put a of t here, So now it represents an expression. If I want to try the plot this way, it doesn't work. Nothing. That's because it's this expression that it already involves t, so don't put another t here. That works. If I do have a t here and get this expression, I don't need a t down there. Okay, so lots of subtle, confusing things. It takes some practice with these things to get it right. All right, let's go on to the differential equation now. Okay, so this is a continuation of the example from the last video. Excuse me. This arbitrary but fixed initial value problem. Here was the code we used to look at the solution in the slope field. And we used DSolveValue up here to store a pure function in this symbol here. We plotted that. We did need the t there. And we saw the plot look like this. And what I want to say here for the rest of this video, just for a few minutes here, is related to the comment I had at the end of the last video here, that when you've got a function here that's a solution of a differential equation that's got a vertical asymptote, our initial condition was for t equals 0. This other piece of the graph you really should not consider to be part of the solution because we want our solution to be unique, and you could, in a sense, translate this graph up and down in a sense. Well, you'd have to modify it to make sure it follows the slope field to get another piece, two pieces of the function that could be pieced together to still solve the differential equation and the initial value problem, but you want your solutions to initial value problems to be unique. So it's probably better here is, I actually don't have to use the exclusions when I do this, is to change the right endpoint of this interval here initially to being where that vertical asymptote occurs instead of 4 here. It occurs at 1 over y0. And there we go. That gets rid of that second piece that comes after the vertical asymptote. However, there's still a problem with this. This works fine as long as y0 is positive. We're only going up to the vertical asymptote and not including the part after the vertical asymptote. But what if y0 is negative? This code that I have up here going from -4 up to 1 over y0 doesn't work in that case, because in the case where y0 is negative, you really want your graph to, in a sense, start at 1 over y0 and go to +4. Alright, that can be fixed, but it's a little tricky. Here I'm going to use this if command, and let's see. Let's do it like this. I'll type it in and then I'll explain it. If y0 is greater than 0, I'm going to make this thing be -4, else it's going to be 1 over y0. Okay, what did I mean when I said what I just said there? If is a conditional operation, a conditional function, it takes this first input and says, okay, is this condition true or not? If it is true, then if gives you, in this case, -4 as the output. If it's not true, else, if it's false, it gives you this thing as the output. So if the initial value for the initial value problem is positive, I want this left endpoint of the interval to be -4. On the other hand, if it's negative, I'm not including the case where it's 0, I want the left endpoint to be 1 over y0. I guess that's technically, the y0 equals 0 case is technically included, but it actually would give an error in that case, so we won't worry about that. The right endpoint can also be described in terms of the if. If y0, the initial condition, is greater than 0, then I want that right endpoint to be 1 over y0. Else, if y0 is not greater than 0, I want this to be +4. And this takes care of both cases, when y0 is positive and when y0 is negative. Okay, in both cases it includes the origin as part of, the interval containing the origin is the part of the graph that you want to focus on. In the case where y0 is 0, I guess it's not going to work, but we will ignore that case, and with that I'll end this video.